Welcome to part 2 of Unit 16. We're going to continue our discussion of the chemistry of the alpha carbon. We're going to pick up where we left off in part 1 with adding electrophiles to the alpha carbon. And in this case, or in these examples, what we're going to look at is how do we alkylate the alpha carbon. And we're going to start with looking at 1,3-dicarbonyl compounds or beta-dicarbonyl compounds. And the reason that we're going to start here is that these hydrogens, the alpha hydrogens, are much more acidic than that of the alpha hydrogens next to a ketone or aldehyde. The pKa of these hydrogens are on the order of 6 to 11 in comparison to 19 to 20 for the alpha hydrogens of aldehydes and ketones. And what this means is that we can use bases such as sodium hydroxide or alkoxide bases and pretty much quantitatively make our enolate. And when we do that, then once we make our enolate, if we treat that enolate with a primary alkyl halide or methyl alkyl halide, it will do an SN2 reaction and we'll add our alkyl to the alpha carbon here. And again, this is under basic conditions, so we're going to form an enolate. And so let's draw our mechanism. We're going to use a generic 1,3-dicarbonyl. So here's the first one. Here's the second. And we've got our two alpha hydrogens shown here. And we're under basic conditions, so we'll have either hydroxide or alkoxide. We'll use hydroxide for ease. We'll come in and abstract one of the two hydrogens, giving us the enolate. R prime, and still have our alpha hydrogen, or one of them anyhow, and now we've got an anion, and we can draw a resonance structure of this anion. Oops, I want to forget my lone pairs. To give us the other resonance structure. Like so. And we've got our enolate, so this is our nucleophile. And if we have some alkyl halide, and here we've got some primary alkyl halide. What can happen is the electrons roll down. That kicks these out. It does an SN2 reaction here. This is an SN2. And what that does is it adds this alkyl piece right here to the alpha carbon, giving us our final product here. Still have an alpha hydrogen remaining, and there's our alkyl piece that's been added. And so under or with 1,3-dicarbonyls or beta-dicarbonyls, this alkylation is very easily accomplished with bases such as hydroxide or alkoxide. So if we look at the alkylation of aldehydes and ketones, it's not as easily accomplished as what we just saw with beta-dicarbonyls. And the reason for that is that even though we have seen or we have discussed that hydroxide or alkoxide bases will deprotonate these alpha hydrogens, which they will, they're still 4 pKa units apart. And in the case of hydroxide, which would be the weaker of those bases, so it would be 15.7, the equilibrium still lies with the keto form versus the enolate. And we need the enolate because that is the nucleophile in this reaction. And so we really can't, under basic conditions where we have hydroxide as a base, we really can't facilitate the alkylation of the alpha carbon of aldehydes and ketones. And so what we need is some base to shift this equilibrium to give us solely the enolate. And we're going to discuss how we can do that, or what base can be used to do that, here in a second. So to drastically alter the equilibrium between the keto and the enolate, we need a very strong base. So we need a base that has a pKa greater than 19 to 20. But that base can't act as a nucleophile. We don't want it to be adding to the carbon of the carbonyl. We just want it to deprotonate the alpha carbon. And the base that we typically use for this is called lithium diisopropyl amide, or LDA, and it has a pKa of 35. And here's LDA, and the reason that we like LDA is that it's sterically hindered, so it will act as a base, but it's so sterically hindered that it won't act as a nucleophile. And so we make LDA through the reaction of diisopropylamine with N-butyllithium at minus 78 degrees Celsius, and we get lithium diisopropyl amide, LDA. And if we then treat a ketone or aldehyde with LDA, we get 100% of the enolate. And the reason is that LDA is much more basic than our enolate, and so this reaction is favored to go in this direction to give us the enolate. So we can quantitatively convert a ketone or an aldehyde to its enolate using LDA. So now that we have shifted the equilibrium to give us only enolate, we can very efficiently alkylate the alpha carbon to an aldehyde or a ketone. So here we've got our generic aldehyde or ketone. If we treat it with LDA first, that makes the enolate, and once our enolate is formed, then we can treat it with our primary or methyl alkyl halide to alkylate at the alpha position. And here's a specific example. If we've got cyclohexanone and we first treat with LDA, we quantitatively make the enolate, and then if we treat it with methyl X, so where X is bromine, iodine, etc., we will put a methyl group on the alpha carbon. So what's the mechanism for this? Well, the mechanism for this reaction is going to be identical to what we've seen previously. Again, we'll use a generic carbonyl. Our base is going to be LDA. It's going to grab one of the two acidic hydrogens. And no, this is not under equilibrium conditions, giving us our enolate. Like so. And we have a resonance structure of this enolate, so we got to draw it in. And at this point in time, we've got our enolate, and it can attack our halide, or our alkyl halide, as so. Swing down, does an SN2 reaction, kicks out X. Giving us our final product as such, or as so. And again, this is an SN2 reaction. So again, we've seen multiple reactions here where we've alkylated or added halogens to the alpha carbon, yet all the mechanisms are the same. All we're doing is changing out what our electrophile is. We started with a halogen, and now we're alkyl halides doing SN2 reactions. So at this point, we haven't seen any examples where we've got substitution on the alpha carbon. And how would that substitution, if we had it, affect the reactivity of adding electrophiles to one side or another of the alpha carbon? So here we've got an example. Here we've got a methylated cyclohexanone, and we have this purple hydrogen here and these two black hydrogens there. And if we treat this with base, we have the possibility of getting two enolates. Enolate here, where we on the unsubstituted side, or an enolate here on the substituted side. And this enolate is actually favored because we have the more substituted double bond, and this is then the thermodynamic enolate, but we form this enolate as well, and this is the kinetic enolate because it's formed faster. So when your base comes in, it's got two options here versus one there, so it's going to grab the least hindered side. It's going to grab these the fastest, and therefore we will form both kinetic and thermodynamic enolates. But let's say we want to deprotonate only the least substituted side. We want to make the kinetic enolate. In that case, what you do is you would use an excess of your base. So you'd use an excess of LDA, and that's going to deprotonate these hydrogens faster, and a majority of our alkylation product then, because we get a majority of the kinetic enolate, we'll get our major product will be addition to the other side to give us this substitution pattern versus a small amount of the di alkylated on the alpha carbon. Now sometimes you want to get the kinetic enolate, and I actually had this issue in my own research where we wanted to get the more substituted enolate. And the trick that you have to play here is that you have to allow the kinetic and thermodynamic enolate to equilibrate between each other, because this is the lower energy enolate. So if you give it time and let the reaction equilibrate, they will funnel slowly down to give you the thermodynamic enolate. And the way that you can do this to set up this equilibrium is to use an excess of your starting material. And what happens is that of course, you add your LDA, you make both enolates, but this enolate is higher in energy, and it will slowly deprotonate some unreacted starting material at the more substituted carbon. And the reason for that is this is a weaker base, right? This has a pKa of 35. These two have pKa's of 19 to 20. And so much weaker bases, they have equal pKa's, and at that point in time, these two enolates can slowly equilibrate back and forth until they you get a majority of the thermodynamic enolate in solution, and therefore when you let that occur, your major product then will be dialkylation at the same alpha carbon. But it comes down to, again, which one's formed fastest and which one's formed is lower in energy, and in these cases you have to let it equilibrate if you want the thermodynamic enolate. A milder way to add alkyl groups to the alpha carbon is through the use of enamines, and specifically what's known as the Stork enamine. And the reason it's called the Stork enamine is it's named after Gilbert Stork, who used this type of chemistry to alkylate the alpha carbon to carbonyls. It's a much milder way to do this chemistry because we don't have to use strong base to undertake the alkylation. And what happens here is, if you look at the general reaction scheme, we take our carbonyl, and with trace acid and a secondary amine, as we saw in Unit 15, we can create enamines, and this is what we call a Stork enamine because of the 5-membered ring pyrrolidine base. And once this is formed, if we treat it with electrophiles, this will add our electrophile to this carbon of the enamine to give us the iminium ion, which, when we work the reaction up, we use aqueous acid, and that will hydrolyze the iminium ion to give us back our carbonyl, but we still have alkylated the alpha carbon to that carbonyl. If we look at some specific reactions, here we've got cyclohexanone. We make the Stork enamine. We react it with methyl bromide, and we'll brominate the alpha position here. We got our iminium ion. We work it up with aqueous acid, and we will hydrolyze off the iminium ion to give us our ketone back. Not only can we alkylate, but we can acylate as well. We can, again, treat this with any electrophile to add to this carbon, but the interesting thing here is we've got an acyl chloride. Again, we make the enamine, and that enamine will attack this electrophile, and we will make the iminium ion plus our electrophile has been added, and again we'll hydrolyze this under aqueous acid to, in this case, give us a beta dicarbonyl compound. So how does this reaction work? Well, the first thing that happens is you form the enamine, which we are not going to show. We're going to start with the enamine and look at its reactivity. And so here's our enamine. Got the lone pairs there, and we'll draw in our electrophile. And what happens here is the lone pairs swing down to form the carbon-nitrogen double bond, and it kicks this out, the electrons from the double bond, which go out and attack the electrophile, kicking out the leaving group, giving us our product. Well, our penultimate product gets the iminium ion. But our methyl group has been added. And this is an SN2 reaction. And from there, this iminium ion gets hydrolyzed with H3O+. To give us our carbonyl back with our electrophile added to the alpha carbon. Now let's take a look at, let me zoom out here, you can take a look at it. So again, it's just an SN2 reaction, form the iminium, which we hydrolyze in the end to give us our carbonyl back. Now what I want to definitely take a look at and show you how it works is the attack of the Stork enamine on the acyl chloride. So if we draw our enamine, so here's our Stork enamine, and in this case here's our acyl chloride, and Reaction's the same. Electrons swing down to form our carbon-nitrogen double bond, kick out the electrons in the double bond, which attack the carbon of the carbonyl. Electrons roll up onto the oxygen of the acyl chloride. Acyl chlorides are excellent electrophiles. That gives us the following. Iminium ion. Chlorine. So we've got ourselves a tetrahedral intermediate here. And they don't stick around very long. They like to collapse if they can. And for them to collapse and to go back to a carbonyl, carbon-oxygen double bond, we have to have a leaving group. And we do. We've got chlorine. So when these electrons swing down, they're going to kick out our chlorine. And that will give us the acylated product, shown here. Still iminium ion. It gives us this, and again, once we have the iminium ion, once the electrophile has been added, when we're done with the reaction, we work it up with aqueous acid, H3O plus, and it will hydrolyze the iminium ion to give us back our carbonyl. And we still have our group, our electrophile attached to the alpha carbon. So there's the product of this. So if we zoom back out and take a look at it all together, storquinamine attacks the electrophile, in this case the acyl chloride. We've now made the carbon-carbon bond. This tetrahedral intermediate, if it can, will collapse, but it needs a good leaving group. It's got one. It's going to kick out the chlorine to give us our carbonyl, so we've acylated in this case, and then when we work this reaction up with aqueous acid, we'll hydrolyze off the iminium ion to give us, in this case, a beta diketone. This brings us to in-class problems 16-1 and 16-2. In 16-1, what I'd like you to do is to show how you could employ enamines to the synthesis of the following compound. So how could you use an enamine to make this compound shown here? And in 16-2, dienolates can be formed from beta-keto esters. So here's a beta-keto ester. So we've got a 1,3-dicarbonyl compound. And if we treat this with 2 equivalents of LDA, we'll make a dienolate. That means we've got 2 enolates on the same molecule. And dienolates can be alkylated selectively at the more basic of the 2 enolates. So what I'd like you to draw is the mechanism using curved arrows of the following reaction. If you notice, we're going to be alkylating at this carbon here because that enolate that would be formed with this carbon and oxygen is more basic than the enolate that would be formed at this alpha carbon between the two. So this would be a good time to pause the video, take some time, work on these, and then we'll come back and do it together. Now that you've had some time to work on this, let's take a look at them. So let's start with 16-1 first. So if you notice here, we've got a carbonyl and we've added some electrophile, which would be this whole piece here, to the alpha carbon. So here is the piece that's attached to this alpha carbon shown there. And so therefore, if we were to create this compound with an enamine, we would have converted this to an enamine right here, and this piece would be your electrophile. And you've noticed there's a carbon there, right? So we'd have to have some leaving group on that carbon. It could be some alkyl halide, some halide, or other leaving group. We'll stick with the halide. So if we were to work backwards and draw the two pieces, well, this piece here, oops, trying to make it Texas Carbon there. This piece here would be the enamine. And like I said, the piece circled here in red would be our electrophile, so I will draw it in red. And we have to have some leaving group here, and we'll just use a halogen, so bromine. And if you notice here then, here are the two pieces. Here's the enamine that it came from, here's the electrophile. So the way you approach this is you look at your compound, you look what's attached to the alpha carbon, that's this piece. This piece would have been added, so this would be the electrophile, and then this piece here, which contains your carbonyl, would have been the enamine. And so here's our enamine, and here's our electrophile. Now let's take a look at the second problem. We're going to draw the mechanism of the formation of this compound, and we're making a dienolate. So we're deprotonating twice. And the reason that we can get away with this in this compound is that we've got two carbonyls. And so if I treat this with LDA, we've got two hydrogens here that have pKa's on the order of 6 to 11. And then you've got hydrogens out here which have pKa's on the order of 19 to 20. They're probably going to be a little higher, especially after we've made the anion here, deprotonated this to make this enolate. But still, we've got LDA, so it's got a pKa of 35. It's a pretty strong base. We'll be able to pull these hydrogens off. So if we blow this up, I'll redraw it. So we got CH3, two hydrogens, pKa 6 to 11. These will easily be deprotonated by our base, which has a pKa of 35. Come in, grab hydrogen. No equilibrium errors because there's no equilibrium here. Not with that strong of a base. And so that's going to give us the following. Right? Let's draw out the resonance structure. And I'll draw one hydrogen down like that, fortuitously positioned. And again, our LDA can come in and act as a base to make the dienolate. And actually, I'm going to make the enolate in one step. You can also draw it this way. This will be the first time I think I've ever drawn it this way in these videos for you. And what that gives us then is our dienolate. And dienolates are more nucleophilic at their most basic side. Well, this is you can think of it as a normal aldehyde or ketone, therefore it's going to be more basic here, and therefore when we've got our electrophile. In this case, our electrophile is the following alkyne. We're not attacking the alkyne, we're attacking the alkyl halide. Like that. Electrons swing down, does an SN2, kicks out our leaving group, and that gives us the final product, which would be the following. After workup. So we'll say H2O. Like so. And you can see here, all we did, the mechanism's the same. Again, we deprotonated, but in this case we did it twice. And that second enolate, the more basic of the two, is the more nucleophilic. And therefore, our first electrophile, or electrophile, will add at the most nucleophilic site, which would be at this carbon shown right here.